In this episode of Woodlands on the Web, we're going to talk about chemical equilibrium and equilibrium constants. You should have this note sheet with you and be ready to fill it out and do the examples with me as we go through this. Okay, first of all, the most important thing is that it is the rate of the forward and reverse reaction that is the same at chemical equilibrium. It doesn't mean that you have the exact same amounts of concentrations in products. Another thing to point out is that these are typically closed systems. This is a closed vessel. Based on the law of mass action, we can write an expression for equilibrium. I want to also mention Q, which is the reaction quotient. So the reaction quotient is just basically the relationship between products and reactants, and this helps us also decide which direction things will shift. So reaction quotient allows us to predict the direction of a Le Chatelier shift, for example. However, in equilibrium, your reaction quotient will equal your equilibrium constant, and that's another way to see that reaction is in equilibrium. You also see this typically as Kc, which would mean the constant of concentration. You might just see K, even though we know in chemistry there are lots of different K values. Kp is going to be with regards to pressure, and then in the future, we're going to look at KSP, which is for solubility potential, as well as Ka, Kw, and Kb, which is for acids, water, and bases. So K is really just your generic equilibrium type of constant. Okay, if we are talking about things with gases specifically, so pressures are only going to affect gases because gases are the only state of matter that can be squeezed and confined into a smaller volume. Solids and liquids both have a definite volume, so pressure is not going to affect them. If we are talking about a system of gases, then we can use our equilibrium constant based on pressure in order to also find our concentration and the constant overall. I do want to point out that this expression here is based on the ideal gas law, which you might remember as PIV-NERT or PV equals nRT. Remember that this is the ideal gas constant, and with that particular one, because it's in units of liters, atmospheres, moles, and kelvins, you do have to make sure that temperature is in Kelvin, so you convert it if you're trying to use that expression. You also need to use pressure in atmospheres if you're using this particular ideal gas constant. You may remember from honors chemistry that there are different versions of it, which basically is due to a difference in the unit of pressure being used for measurement. Just to clarify this here, where it's talking about moles of product minus moles of reactant, that's literally just using the coefficients in the equation. We'll see an example of this in just a minute. Okay, so for our first example, let's just write our equilibrium constant expression. So overall, or in general, I should say, this is just going to be the concentration of our products over the concentration of our reactants. We're going to also raise them to a coefficient based on whatever coefficients are in front of them. So again, if we look back at this expression, this one here, you see that the lowercase letter is being used as a power for the substance that's the capitalized letter. I also want to point out that this is multiplication, not addition. So even though things appear to be added in a balanced chemical equation, when you're dealing with an equilibrium expression or a reaction quotient, which are written the same way, you are going to eventually be multiplying those if you actually have numbers to use. Okay, so back to this example. Because these are our products, those are going to be on the top. And because these are our reactants, these are going to be on the bottom. Okay, you should probably be given states of matter with respect to things like this. But considering that you're looking at ammonia and oxygen gas, then you can pretty safely assume that these are all going to be in the gas or vapor state. Something that's important to note is this statement right here. If things are pure solids or pure liquids, they're never used in equilibrium expressions or in reaction quotient expressions because they are constants. Things that are aqueous solutions or gases are the only things that can be adjusted or shifted in an equilibrium system. So they're the only types of things that are important to those expressions. Okay, so again, for example 1, we can pretty safely assume that these are all going to be gases. So in order to write out this equilibrium expression, then we would put our KEQ equal to our concentration of nitrogen dioxide raised to a power of 4, which is simply the coefficient from the balanced chemical equation. And that's going to be multiplied by the concentration of water to the power of 6 over the concentration of ammonia to the power of 4 and the concentration of oxygen gas to the power of 7. Okay, so again, this is called your KEQ expression. So if you're asked on the AP exam to write an expression, this is what you should have, and you should not have any math involved. Okay, if you are looking specifically at the KEQ for a reverse reaction, then it's kind of a silly idea, but you're still going to do it the same way. So if you're looking at the reverse reaction specifically, then in this case, A and B become your products, and C and D become your reactants. So that being said, you would actually have A concentration to the power of little a times the concentration of B to the power of little b, concentration of species C raised to the power of the little c, even though that doesn't really look little, and then the concentration of species D raised to the power of whatever the coefficient in front of D is. Okay, lastly, if we take our expression or our balanced equation and multiply it by some similar number, so in this case n, but let's say we just multiply everything in the original reaction by 2, for example, then if we were writing that out, it would look really similar to before. So you'd have concentration of C, but now it's going to be to the NC. Concentration of D to the ND, A to the NA, and B to the NB. Okay, so that being said, you can actually just take the N's out, and you're going to have the equilibrium expression. Let's call the initial one K prime. So if we take out the N's, I'll fix that in a second. So if we take out the N's and just use what our initial expression would be, so let's call that K prime, then K prime raised to the power of N would be your expression. So for example, if you found out that your original equilibrium constant equals, let's just say, the number 2, if you were to multiply the entire balanced equation by 2, by a power of 2, then this could be your K prime value, and K would then be 2 squared, or 4. Okay, it just allows you to easily add the power that the factor is being applied. Okay, I'm going to go ahead and stop there, and then we'll talk about equilibrium position and the rest of this in just a minute. So go ahead and take a break, pause, and get on to the next video once you're ready to move on.